Hello and welcome to the second video of the D1 chapter Graphs and Networks. Start a question on the screen. Draw a graph that satisfies these conditions. It must be connected, have 4 odd vertices, 3 even vertices, 11 edges, one of which is a loop. One possible answer is about to flash on the screen. Pause the video now if you want to give this a go first. Here is one possibility, but there are many. I need 3 even vertices. This one is order 4. This one is order 2, and this one is order 4 because the loop counts as 2. The others are odd. 1, 2, 3, 4 of those, because there will always be an even number of those. If I had said 5 or 3 of these, it would not have been possible. And you can see that it is connected. There's no vertex left by itself without being connected in with the rest of them. In this video, we're going to look at a couple of special graphs, which means more terminology. Straight in, a complete graph is a graph that has all vertices connected to all other vertices. So a really simple one. Obviously 2 would be that, 3 would be that, but then it gets a little bit more interesting with 4 because it's not just this, but it's also these 2 lines here, and so on and so on. Interesting side note, if you space these around a circle, you would get something sometimes called a mystic rose, a very pretty geometric pattern. The complete graph with n vertices can be written as k subscript n, so this would be k4. That's because although there are different ways to draw this, it's kind of showing you the same information. If I did, for example, 3 and then 1 in the middle, connect these 3 and connect these like this, each of these is connected to the other, and each of these is connected to the other. It's not showing you anything different. It looks very different, but the information is the same as a graph. So if I say a complete graph with 4 vertices, there's only one graph that really satisfies that, even though you can draw it in different ways. That leads us into the next term, because these two, which are the same graph drawn in different ways, is called isomorphic. Graphs that look different but show the same information. It's easy with a completed graph to see that because everything's connected to everything, but with any other graph you can get isomorphic graphs as well. Proving that 2 graphs are isomorphic can be really quite a pain, but drawing them is not too bad. So here, K5, a complete graph with 5 points. I kind of space them more or less as if they were on a circle. And connect this one with all of these, connect this one with these, connect this one, and I should have done it more systematic than that. Is that it? Everything is a valency of 4? Yes. Okay, if I want to do another one that's a complete graph, I'll do something similar to what I just did on the previous screen. Around the edge here, and then connect in the middle, but you've got to be a bit more careful here, because that is not finished yet. I have not connected this top right corner with this bottom left corner. I've connected them here. In order to connect those directly, I would also want this and this. And that brings up an interesting point that's worth noting. If 2 lines cross but there's no vertex, they are not considered to be connected. Same as all of these, you wouldn't consider these to be connection points. They're not vertices, they're just where 2 lines happen to cross in order to be able to draw them. So these are both K5 graphs. They are isomorphic, they're showing you the same information, but they do look very different. A tree is a connected graph with no cycles. So on the bottom here, you can see that we have a cycle here, we have another cycle here, but a tree has no cycles. If I were to draw an example, something like this, this is a tree. There's no way to cycle in this graph. If I connect here, then I could, and it would be a cycle. So this is a tree. This is another term that comes up in a later chapter in a very specific way. It comes up as what is called a spanning tree. And a spanning tree of a graph is a tree, obviously, that is also a subgraph and one that uses all the vertices in the original graph. So I'll use this one here, and I need all of the vertices. That's important. So I'll get them all there. Now there's lots of different options here. There is not one answer only. It's kind of already a subgraph by default because I've used just the things so far that are in here. It's using all the vertices. It needs to be a tree, so I can't have any cycles, but it must be a subgraph. So I can't go connecting A and C because there is no connection between A and C in the original graph. So I could connect C with B and D and E, but then I would have to connect A to either B or E. Let me connect it to B. So there is one possible spanning tree of this graph. Another example of that, to finish, draw two possible spanning trees for the following graph. So we need all of the vertices. Maybe I should have done one with fewer vertices. A, B, C, D, E, and F. Connecting that, yes, that is okay, that's okay, that's okay, and then to get C in there as well with no cycles, there we go. There's one option. An alternative, you could do very similar trees to that. For example, you could do all the same outside edges, this, and then connect D to C instead of B to C, and that would be a different spanning tree. But I quite like mine to look a little different when I do two different options. So let's connect A, E, E, F, E to C, C to B, and C to D, something like that. There's a very different looking spanning tree. That is most of the terminology done now, and that should be enough for you to have a go at the questions in exercise 2C. And maybe I'll see you in the final video for this chapter.